Chapter 8, Advanced Algebra, and in this lesson, in this chapter, we'll be looking at exponential and logarithmic functions. They are inverses of each other. We'll take a look at the exponential function first, and the exponential function we can use to model population growth or depreciation. Depreciation simply meaning the decrease in value or the decrease in size of something. And then we'll take a look at the logarithmic function, which is the inverse of the exponential. So in the first lesson here, we'll be taking a look at the exponential model. We want to be able to model exponential growth and decay. And when we say model, we mean we want to be able to write an equation that represents specific data that we're looking at. And then also we want to be able to graph that, or to know what the shape of the exponential graph is, and then apply what we know about graphs, graph transformation, right or left, up or down, reflection, stretch, strengths, those types of things, to make quick sketches of these graphs. Once we kind of have an understanding of that, we want to be able to apply that then to different models or different situations, such as car depreciation or population growth. So let's begin by taking a look at the exponential model. Now, what I have here, I have the algebraic model and the graphical model. The algebraic model here is y equals a times b to the x. And an exponential function is a function where the variable is part of the exponent. Okay. Now, we haven't had this before in most of the, well, in all of the functions that we've dealt with so far. The base has been the variable x, x squared, x cubed, cube root of x, x to the 1/2. So the base has been the variable, and then we've had a real number as the exponent. The exponential function switches that a little bit, where the variable is part of the exponent. Now that creates a little bit of a problem for us, because we can't solve these equations then when the variable is in the exponent. We don't really have a way to get that variable out of the exponent yet. And actually the logarithmic function is going to be the tool that we use to solve that, but that will come later. So the algebraic model is we have y equals a times b to the x, and as we've talked about before, this represents a relationship between y and x. A and b have to do something or apply to the actual data. And so we have to determine what the value of A is and what the value of B is, so that when we substitute an X value in, we get the appropriate Y value. Now there are a couple restrictions to the values of A and B. A cannot be 0. And if you think about it, that makes sense, because if A was 0, this is a times b to some exponent. If a is 0, we're going to be multiplying 0 times that b to the x, which makes the entire thing 0, which isn't going to really apply to anything growing, because every number we put in for x, we're going to get 0, so that doesn't work. The b value, which is the base of the exponent, meaning the x, the number that we put in for x, we're going to raise b to that power. If you think about it, this also makes sense. If b is 1, b to squared is 1, b to the 100th power is 1, b to the 1,000,000th power is 1. So if the base is a 1, then substituting in different values for x isn't really going to give me any other y value other than the number 1, so it's not going to be very applicable. So y equals a times b to the x, this is the algebraic representation of an exponential growth, so we're going to need to determine the value of a and then the value of b. That's going to be our task. As we look at the graphical representation of that, this is what an exponential growth looks like. And you can see it's very small on the left here, but as you go to the right, as the x values get bigger, then this starts to grow, and the further right you go, it grows quicker and quicker. So this is an exponential growth. You remember a linear equation has a very steady growth. In fact, it grows the same rate no matter what. Over 1, up 1, over 1, up 1, over 1, up 1, or if a slope of 2, up 2 over 1, up 2 over 1, up 2 over 1. So it's a very steady growth. With an exponential growth, as you go further, it grows quicker and quicker, because you're raising that b power to higher and higher power. So the growth is much quicker when we're talking about exponentials. Now there's one new word here that I want you to realize, and something that we're going to have to use when it comes to exponential functions as well as rational functions in later lessons, and that's this word asymptote. Now asymptote is a line, and it's an imaginary line that a graph approaches as x or y increases in value. So in other words, this blue line here represents an exponential growth, and you'll notice that it gets down here close to 0, and in actuality this graph never actually touches or never has a value of 0. And if you think about that, that makes sense, because if we're using exponential growth to model something that's growing, you have to have something to begin with. You can't have 0 and then just growth start from nothing. So the exponential growth function can never be 0. So the graph is going to start at a very, very small value close to 0, and then as you move to the right it begins to grow, and then again, as we said, grows quicker and quicker. So this asymptote is this line, in this case the line y equals 0, which is this line, it's imaginary, that the graph will get very, very close to but actually never touch. And that line, that horizontal line, wherever it is called an asymptote. Now we also have vertical asymptotes, but again, we'll look at that in coming lessons. Based upon our definitions, if we have a x as part of the exponent, the equation is an exponential function. If the variable is not part of the exponent, it is not an exponential function. So let's take a few examples and see. Would this be an exponential function? The answer would be no, because as we look at the exponent, there's no variable. The variable is the base. This is something we've done before, so this would not be an exponential function. What about this? Would this be an exponential function? Again, no variable as part of the exponent, so no, this is not an exponential function. Is this an exponential function? Well, the variable x is part of the exponent, so therefore this would be an exponential function. Is this an exponential function? Again, the variable is part of the exponent, so yes, this would be an exponential function. Okay, so that's what an exponential function is. Those are the parts of it. In the coming videos, we'll talk about how we determine the value of a, how do we determine the value of b, and then how do we graph it, and then how we can use it to model different situations.